Good morning, Emmanuel. Thank you for being with us again today. Today is your lecture number 4. Yeah. Yes. Sorry. I have the program next to me. I forgot the count. But today we start. No, yesterday we started round 4. Yeah.
Sure.
Okay, so good morning also to the participants. Thank you very much for being with us so constantly. That's absolutely fantastic. I admire the resilience. And Emmanuel, people are not here to listen to me wasting their time. You're welcome to share your screen and start. Yeah, we are all looking forward to the next round. Yeah.
Great, thank you. Let me just get organized. Okay, great. Okay, so in our previous session, we had a gentle introduction to CNNs. And I hope some of you took some time to try this out because it's, really incredible. So just a reminder, so an image is made up of pixel values, and a color image is made up of 3 matrices stacked on top of each other: the red channel, the green channel, and the blue channel. And each of these matrices will have values between 0 and 255. And then I explained that commonly we normalize the values to 0 and 1. And one way to do that, because the range is between 0 and 255, is to simply divide by 255. And then, we discussed the idea that we could solve an image classification problem by just creating really long vectors from the pixels. So you take the first row and the second row, and then you map it into a really long vector. So you could, in theory, tackle it using a feed-forward neural network. But then we explained that CNNs are state-of-the-art, and we'll now explain how it does this idea of finding something in an image regardless of the location. So we spoke about this last time, but we didn't get into the details just yet. Something we also spoke about is how the idea of how humans abstract and how CNNs essentially learn how to do a similar abstraction by doing nonlinear combinations of what comes before it, and how CNNs learn essentially simple things. And then we combine these simple visual features to learn more and more complex features. So we spoke about this last time as well. Now I'll slow down. So essentially, we said that we have an image and we apply a convolution operation using some filter to generate a feature map. And then I showed this little example where if you have an image and then you multiply, so if you take the 9 values in the corner here and you multiply it and you take the dot product with this filter, you'll end up with something like this. So now, all right, and then we had a little introduction to what the filter looks like. So just a reminder, the filter has a particular width and a particular height. These are user-defined parameters, and inside the filter are the weights. So these are what we're trying to optimize. Okay. So that's where we left off. So previously, what we saw was that the feed-forward neural networks had these nodes and these edges, and the edges contained the weights. So remember, we had like an input node and we had an output node, for example, and there were the weights, and the idea was to optimize for these weights. Now that was with the fully connected layers, but with convolutional neural networks, we make use of filters. And in the filters, the weights are inside the filters. So with feed forward layers, we're optimizing these weights, and it's visually depicted like this. And with CNNs, we are optimizing filters, and we depict the weights like this. And the nice thing is that this representation allows us to create filters that learn about that become spatially independent of the location of what we're trying to find. So how is the filter applied to an image? This is probably the one takeaway message that I would like you to take from this lecture. So let's say we have an image and it has a particular width and a particular height, and it has, and so we agreed that an image is just a matrix, and it contains all these pixel values, and the pixel values range between 0 and 255. So here I've just randomly written some pixel values. So this is the top left corner of the image, and here are some values between 0 and 255. And I didn't fill everything in, but you can just imagine that it's all filled in with pixel values. So how it works is you would have a filter, and the filter contains the weights. So here's a 3x3 filter. And just like with the fully connected layers, the weights are randomly initialized. So the weights of the filters will also be randomly initialized. So in this case, I've just randomly made up values. So here's our filter with some randomly initialized values. So what we do is we take our 3x3 filter, which is here in dark blue, and our image, which is a little bit in lighter blue now, and you just put it in the top left corner. So you take the filter and you place it in the top left corner. And since your filter contains weights, right, and the image contains pixel values, there will be one weight which will correspond to one pixel value. So there'll be a mapping. So each weight will correspond to exactly one pixel value, and then you can multiply these. So the filter weights, the values in the filter, when you place it on the edge of the image, are multiplied with the pixel values. So how is this multiplication done? So here is the same image with some pixel values, and here's the same filter that I showed you just now in the bottom left. So this is how we do it. Since we place it in the top left, we say 3 multiplied by 3 plus 1 multiplied by 4 plus 0 multiplied by 1. Okay, so now we've done this row. Now we do the next row. So plus 2 multiplied by 1 plus 0 multiplied by 0 plus 4 multiplied by 40. Now we've done this row. Now we do the last row in the filter. 1 multiplied by 3 plus 1 multiplied by 9 plus 3 multiplied by 16. Now we've done all the values in the filter. We now compute the answer. And that is essentially this expression that I showed you earlier, where the result of this calculation will be our first value of f. So x in this case is the image, w is the filter, and this dot product was one operation of the convolution. Okay, so is everyone okay with applying the filter the very first time? So we'll do another one, but I just want to see if everyone's okay with. So is that a question? Eric, do you have a question for the?
Sorry, Yes, I have a question, but Martin, you can go ahead.
Oh, all right. No, I just want to ask you, like, when we randomly assign numbers to the filter matrix, are we also supposed to use like a uniform distribution, since we are saying the pixel values ranges from 0 to 255, or we can just use any minimum and maximum value?
Yeah, so that's a good question. And let's talk about that a little bit. So this is a whole area of research in itself, the good weight optimization. So there are many optimization techniques. The most commonly used one is called the Xavier initializer. I can't remember the exact formula. I think it's 1 divided by the square root of some parameter. I can't exactly remember which parameter, but essentially you end up generating values between 0 and 1. So usually we'll randomly initialize some values between 0 and 1, or you could have you could just draw from a normal distribution with a mean of 0. So you will typically generate values somewhere between 0 and 1. But there are many ways to initialize, and it's an area of research in itself. So if you're interested, you can explore that. But for the sake of your question, the values will be drawn from maybe a normal distribution.
Thank
Is
you.
that okay?
Yes, yes. Thank you so much.
Okay, Eric?
Thank you so much, Emmanuel. Just a quick question. From what you've just done, what you've just demonstrated here, you're using the formula F is equals to X by W, but I see at the end of the day, maybe mathematically we can put it as F is equals to the sum of Xi Wi. Would that be correct?
Well, it would probably require a double summation, and the next slide will explain why that's the case. So it is Xi Wi in this case, but we will end up moving the filter. So the sum of Xi Wi will not cater for the moving of the filter. We would need to make it a little bit more complicated. So this convolution operator assumes we can move the filter around, and I'll show you how we do that in the next one.
Okay, thank you.
Okay. Any other questions maybe so far on what we've done? If a question, just do a hand raise, otherwise do a thumbs up if you're okay. Okay, great. Okay, so that was the first iteration of putting our filter in the top left corner, and that generates our very first value for our feature map F. So now we're not done. So when we do this convolution, it generates a pixel value for the feature map. So we have our feature map, and it generates the first value. So don't worry about what is the width and the height of the feature map just yet. Just focus on the application of the filter to the image in the top left corner has generated our first feature map value. So that's the takeaway on this slide. So when we do the multiplications of all the values and we add them all up, we get 235. So that's our very first pixel value in our feature map. The other values have not been defined yet. So now the convolution operator, how it works is we move in strides. And when we move one step to the right, we say we're taking a stride of 1. And the stride is a hyperparameter. So the user can say, I want to jump by 1 pixel, or I want to jump by 2, 3, 4. It's up to you. So if we jump by 1, we move everything to the right. And if we jump by 2, we move the whole filter by 2 steps to the right. In this case, we have a stride of 1. So we just move the filter 1 step to the right. And then we do essentially the same thing, where we multiply all the values in the filter with all of the pixel values. So we'll multiply 3 by 4, 1 by 1, 0 by 20, 2 by 0, plus 0 times 40, plus 4 times 50, plus 1 times 9, plus 1 times 16, plus 3 times 33, and we'll get an answer. And that will be the next value in our feature map. Once we've done that, since our stride is 1, we move 1 step to the right again. And we'll keep doing this again and again until the filter reaches the right side of the image. Then we can no longer take a step to the right. What we do then is the filter goes all the way back to the left and now takes a stride in the downwards direction. So here. And because my stride is 1, I'm taking 1 step downwards. So if the stride was 2, we would be taking 2 steps in the right direction until we reach the edge. And then once we've reached the edge, we would take 2 steps downwards. Since the stride in this case was 1, we were taking 1 step to the right. And then once we've reached the edge, we go all the way back to the left, and then we take 1 step downwards. So now we are 1 step downwards, and we will do the same thing, multiply the values in the filter with the values in the image, and we'll add that all up. And then we'll do this again. We'll take 1 step to the right, 1 step to the right until we reach the end. Once we've reached the end, we go all the way back to the left and then go down again. So you'll see that the filter essentially moves around this whole image. So let's look at the top half. So let's say so I'm just seeing a message in the chat. Joseph, can you not see the screen? Joseph, can you?
I can see the screen perfectly.
Okay, so Joseph, maybe if you exit the call and try come back in, you might be able to see.
Yeah, that's what he's suggesting to do. Yeah.
Great.
No, it worked perfectly since the beginning. Otherwise, I would have said something. Yeah.
Great. Okay, so if we look at the top half of this picture, we have a 5x5 image, and we have a 3x3 filter. And here's our little convolution operation. So if we convolve this filter onto this image, this is the resulting feature map that you get. So you'll see that the feature map is a little bit smaller than the original image. And that makes sense because we place our filter and then we move 1 step and we move 1 step. And once we reach the edge, we stop. If instead we wanted the feature map to be the same size as the image, what we could do is we could pad the image with zeros around the image, and then we place the filter at that top corner, which would contain zeros around. And if we did that, the resulting feature map would be the same size. So There are certain cases where we would like the feature map to be the same size, but it's just a detail. I don't want to stress too much about that for today. Let's just focus on understanding instead. So here you can see in the bottom part, I placed the filter in the top left corner, and I did all the multiplications and additions, and I got the first value of 3. And then you keep shifting the filter to the right. And then here you'll see in this instance, eventually my filter reaches here and it produces this value of 1. And then we eventually reach our last operation in the bottom right corner, which produces this 3. So is everyone happy as to how the filter is applied to an image to generate the pixel values in the feature map? In other words, are you happy with the idea of convolution, that we have a randomly initialized filter that contains weights, and we convolve the filter onto the image by multiplying the values within the filter with the values, the corresponding values in the image, and we sum up all those values to generate pixel values in the feature map? That, if this is the only thing you take from this lecture, I would be very happy. So can we just check, is everyone happy with this? So if there are any questions, just put a hands up or unmute.
There are
okay, how's everyone else? So I've only seen maybe 3 thumbs up. How is everyone else doing?
Emmanuel?
Yeah.
Yes, I just want to check something. I'm not very sure. So I see how you generated like in the feature map, how you generated the 3, and then you move across one step to generate the 0, and you then move across to generate the 2. Then you come back and shift down, and then move forward. Then you generate the 2, and then you shift across to generate the 3 and the 1. But I'm not sure how you get to the bottom, because I think the 3 by 3, if you put it there, if you put it down 2 steps, you go to the edge. How then do you generate the last line?
Yeah, okay. Let me try and help you with that. Okay. Let me try and see if I can quickly do a visual explanation. What happened to my picture? Okay. Okay, so let me get rid of that. So sorry, I don't have my digital pen, so this is going to be a bit rough. But okay, let me try to do this. So in where is okay? So we started here and we got the 3. Then we moved 1 step to the right. We got the 0. And we moved 1 step to the right and we got the 2, right? So you were happy with that. And then we jumped down. So we put it here and then we generate the 2. We jump to the right, we generate the 3. We jump to the right, we generate the 1. And then we move all the way back down and we take 1 step down. So it actually fits.
Oh yeah.
So that's how we generate the 1. That's how we generate the 1. And that's how we generate the last 3. Is that, are you okay?
I'm okay now. Yeah. And that explains why the feature map is smaller than the image.
Exactly. If you wanted the feature map to be of the same size, you could you could pad this image with zeros. So something like this, something like this. This is a bit rough. And then you could start there. And then you would move like that. And if you did that, you would see that the resulting feature map would be of the same size.
Yeah, thank you so much. So the filter necessarily has to be smaller than the image. Can it be the same size? No.
Okay, so let's think about that. This is a little toy example of a 5x5 image, but in practice, your image might be 256 by 256. Remember, our goal is to, I've lost my present. Okay, here we go. Our goal is that what we want is to achieve this, is we want to create these simplistic things that when we combine, they learn more complicated things. So if we task the first, the CNN to learn one big filter, then that's too complicated, because we won't be using the idea of abstraction. So if the filters are small, we can generate many. We can learn specialized filters that learn these simple things, and each filter, subsequent filter, will generate smaller specialized things. So you can think of the filters as doing a very specialized visual task. But if the filter was the size of the image, then we're back to square one, where we're trying to solve this complicated problem, and we won't be able to do it. So by having many small filters, we can combine these small things together to solve the problem. So that's the idea, is we have many small filters, and when we combine them, we can solve this more complicated problem. Is that okay, Eric?
That's fine. Thank you so much.
Cool. Are there any other questions about this part? Okay. So we have actually, yes, now I remember, this was an exercise. Here is an image, and here's a 2x2 filter. So what I would like you to do is to apply this filter and convolve it on this image using a stride of 1. So jumping by 1. So maybe take 5 minutes and apply this filter to an image. And when you're done, you can just say in the chat that you're done, and then we can start comparing answers. So when you're done, don't put your answers in the chat just yet. Just say that you're done with everything, and then we can compare. Okay, so 2 more minutes. Okay, 1 last minute. Okay, time's up. I feel like I'm invigilating an exam. Okay, so okay, let's just go in order of those who've said they were done. So Isak, can you, if possible, unmute yourself and explain how you got the first row in the feature map?
Okay, after applying the filter on the first row, I did examine. So the first, looking at the first filter, I got that 877. So moving to the next row, I got 1254.
Can you explain how you got just the first row? So how you got your 877?
Okay, so applying the filter at the left corner, I had 2 times 2 plus 1 times 1 plus 1 times 3 plus 0 times 2. And that gave me 8. So I moved to the next one and I had 2 times 1 plus 3 times 1 plus 2 times 1 plus 0 times 0. That gave me what? 7. So moving to the last stride or last. I forgot the term. Moving to the last side, I had 3 times 2 plus 1 times 1 plus 0 times 1 plus 2 times 0, and that gave me 7.
Great, thanks. Is there anyone who did not get those values? So if you did not get those values, just let us know. Or if you're unclear how to get those values. Matt, you were second. Could you explain how to generate the next row values in the feature map?
Yeah, sure. So yeah, that's the basically multiplying the upper left triangle, and every top left one gets times with 2. So starting with the middle row, okay, it's 3 times 2 plus 2 plus 4, which is 6 plus 6, so that's 12. And then the middle block, which is 2 times 2 plus 0 plus 1, which is 4 plus 1, and that's 5. And then the bottom right square, which is 2 times 0, 0, and it's just 2 plus 2, which is 4. And I'm ignoring the bottom right one each time because it's 0 times each time. So, and then that's a 4, so it's 12, 5, 4.
Okay, is there anyone who did not get those values or does not understand how to get those values? Or let me do the inverse operation. If you got all those values, can you put a thumbs up?
Yeah, we have 4 thumbs up.
Okay,
Guys,
so
it doesn't cost anything to raise the thumb. Eh? 5. Okay, there are more and more. Now they're coming. Yeah, perfect.
okay. Great. Okay. Okay, so I will take it that everyone is comfortable with how we apply, how we convolve a filter onto an image. And if if you're tired this morning and this is the only thing you take away, I'll be very happy. So if this is what you get from today, that's fantastic. So now how do we combine the input image with the filters that we've been speaking about to produce a classification model? So we have our image, our input image, which is the picture of a mountain. And then we have multiple convolution layers, right? Just like with our feed-forward neural networks, where we were allowed to have multiple layers. With convolutional neural networks, we are also allowed to have multiple convolution layers. So let's take our first convolution layer. And now this is where things get a bit messy. So here you'll see that I've decided that in my first convolution layer, I want it to be a 3x3 filter, and I want 20 of them. Now, the 3x3 filter was a user-defined parameter. I decided I wanted the filters to be 3x3. In addition, I decided I wanted 20 of them. So you also decide how many filters you would like to create in a convolution layer. So the idea is we'll have 20 of these 3x3 filters, and each of the weights in the 20 3x3 filters will be optimized during the training of the convolutional neural network. Now, Each of these 20 3x3 filters will produce essentially 20 feature maps, because we saw that one filter produced one feature map, and we just walked through the process of generating a feature map. So if we have 20 of them, then we'll essentially have 20 feature maps, right? So the output of our first convolution will be 20 feature maps. And we also saw that when we apply the filter to the image, the resulting feature map is a little bit smaller than the input. So let me draw that. So if we have our input image, and which is maybe it has a particular width and a particular height, we don't care. Let's say it's a picture of me. And we have our first convolution layer. And our first convolution layer, we decided as a human that we wanted 20 filters, and we wanted each of them to be 3x3. So when we apply our first filter, we will get something a little bit smaller for the reasons that we've discussed. So that's our first filter. And then we have our next filter, which will generate another feature map of the same size, and another one, and we'll have essentially 20 of them. So what we can do instead is we can stack these on top of each other, and we can create a nice little object like this, which will have a particular width and a particular height, and it will have a depth, right? It'll have this particular depth. And do you agree that the depth essentially will be equal to 20? Because each of these 20 filters will produce one feature map, and we can stack them on top of each other. So here's the first one, the second one, and the third one, and so on and so forth, until we have our last one, which will be somewhere there. So do you agree that the depth of the resulting object of applying 20 3x3 filters will produce an object with a particular height and a particular width, and the depth will be equal to 20? Can you let me know in the chat if you are happy or not happy that essentially the depth will be 20? Okay, so Eric agrees. Do the rest of you agree? Right. So this was our first convolution operation on the image. This was our input image. Sorry, I don't have my digital pen, so it'll be with the mouse. So this is our first convolution operation. Now we can see from the slides that I've decided, well, I want another convolution layer, but this time I want 40 filters, 3x3. So remember in our lecture the other day, we said that the output, if we have a feed-forward neural network, that the output of the activation function becomes the input to the next layer. So if we had a neural network, so apologies for the diagram, I don't have my pen. We have our input, we multiply the input by the weight values, and we have an activation function here, which becomes the input to this layer, right? So we spoke about this. Now, once we've generated these values in the feature map, we mustn't forget that we also have an activation function. So we could apply an activation function on all of these values. So here, when you applied the filter to the image and you generated 877 and all your other values, you actually still need to apply an activation function on top of that. So once you've applied the filter to the image, you still have to apply, for example, a ReLU activation function. So here we would still apply our activation function. Perhaps it's the ReLU activation function. So remember what ReLU looks like. Let's use some different colors. So ReLU looked like this, something like this. So we would apply our activation function on all of these values. So now we were done with our first convolution operation. So the convolution operation, it needs to know how many filters you're creating. It needs to know the size of each filter, and it needs to know which activation function you're going to use. So now we've decided that our next convolution layer will create 40 filters. Each of them will be 3 by 3. So now, so Isaac, you have a question?
Yeah, please, I would like to know how is the ReLU activation function applied, because looking at it, I mean, the depth we have 20. So I don't know if it's going to, the ReLU is going to take one, I mean, one feature map at a go, or I just want to like to know how the ReLU activation function is used.
So the activation function will be applied to every single value in the feature map. So the feature map will be made up of all these pixel values for each depth, and we applied the ReLU function to every single value in the feature map. Does that make sense?
So it's like one feature map at a go.
Yeah, one feature map at a time. We'll apply ReLU to every single value.
Okay, I get it now.
Okay. Are there any other questions? So the next step will get a little bit messy, but I'm hoping that you have your thinking caps on and you're holding onto your chairs very tightly. So the next step is a bit messy. So here, one thing that I did not, the assumption we made with our input here is that it was a grayscale input. In other words, the depth was equal to 1. So the depth was equal to 1. So my filter was just a two-dimensional matrix, and I could just multiply the values and produce each value of my feature map. Now it gets a little bit messy. In the next convolution layer, the input is now W by H by 20. So can anyone take a guess, if I apply convolution on this input, because now this is my new input to the next layer, what do you think the depth of each filter will be? So we know that the filter will have a width and a height, but what do you think the depth of the filter will be? Does anyone want to take a guess? So this is our 3 by 3, but what do you think the depth will be? Does someone want to take a guess?
Yes, can you come again? Can you come again with a question?
So the question is, in our initial example, right? So in this part, we had an input image which had a width and a height. A width and a height, and it has a depth of 1. I assume that it was a grayscale image. So a grayscale image has a depth of 1. So our filter will have a width and a height and a depth equal to 1 as well. So we can multiply all the values nicely, the way we've been doing it, the way we've done it so far. This image has a depth of 1, this filter has a depth of 1, and we can comfortably multiply all the values with no problem. So my question is, now that we've generated this feature map, which has a particular width, a particular height, and a depth of 20, what should my filter look like? Will it have a depth of 1, or will it be a different depth? So Eric suggests a depth of 20. What do the rest of you think?
I should guess 20.
Okay. What does everyone else think? So everyone type in the chat, do you think it's 1, 2, 3, infinity, negative infinity? Take a crazy guess. Take any guess you want, but everyone please make a suggestion as to what you think the depth of the new filter will be. Okay, so there's 2 suggestions of 20, there's a suggestion of 1, suggestion of 10, 1. Everyone else, what do you think? Unfortunately, doing it this way creates a bias in that when a popular answer comes, people will suggest a popular answer. So don't look at the previous answers, take a guess and then type it in the chat. Okay, so someone says it might be arbitrarily decided. What about everyone else? What do you think the depth of the filter will be when I apply it to this feature map, which is now the new input, right? This is the new input for our next convolution operation. Okay. Okay, someone suggests 9. What about the rest of you? Okay, so I'd like everyone to participate. If you want to be creative, you can say that it's epsilon, and epsilon must be defined to some small value. Feel free to say anything. Okay, there's another suggestion of 20, 16. Someone says 1. Okay. Okay. So Eric and Matt have...
Just repeat the question again. What was the question? The question. What was the question? Sorry. Yeah.
So the question is, now that we've applied our first convolution layer and we've generated our very first feature map, right? So this is our very first feature map, which is the result of applying the convolution to the input. What will be the depth of the filter if I apply new filters onto this feature map? Sorry. So I want someone else to participate. Let me see. Okay, so Eric participated, Martin participated, Matt, Charity. So Isaac, Charity, can you potentially explain why you think it's 20? If you can unmute yourself, if you have a mic. Okay.
Emmanuel, I just asked Charity to unmute, but
sure, that's okay. That's okay. So let's go in order of who answered.
Now, here we go. Yeah.
Okay, go for it.
No, it doesn't.
Okay. That's fine.
Sorry, I tried to force to unmute, but it doesn't work.
That's
Sorry.
fine.
Maybe
Eric,
there's an issue with the microphone. Yeah.
So Eric, you were the first person to give an actual number. Can you explain why you think it might be 20?
Okay, what I think is already we have, when we applied our first convolution, already we have a depth of 20. So if we want to apply, so already, so this is where I'm taking it from that already. In our first convolution, we created a depth of, because we had 20 images, so we already have a depth of 20. Yeah, so that's where I'm taking it from.
Okay, but why do you think it's 20? Could you think of a mathematical explanation as to why 20 and not something else?
Yeah, I'm not sure.
Okay, that's fine. That's fine. That's fine. Okay, so the second person who said 20 was Matt. Do you maybe have an explanation as to why you think it's 20?
Yeah, I'm unsure, but I think that keeping consistent with striding, if you have a depth of 20, maybe that's then just easier from some mathematical sense, like still just going in 2 dimensions. So you don't have to go in a 3rd dimension if it's less than 20. I think,
okay.
I'm not sure, I'm guessing.
Okay, I can accept that as an answer. So if the filter had a depth of 1, it wouldn't work. If the filter has a depth of the exact same depth as the input, then we can take this. So let's say it has a depth of 20. Then when we multiply, so remember the convolution operation takes the filter and it convolves it on the input. So if the depth is also 20, then when we multiply the values, this can fit snugly in there, and we can multiply every value in the filter with all the values, the corresponding values in the input for each channel, right? So this can multiply with all those values in the input. And then we can move it. We can move 1 step to the right, 1 step to the right, and then we can go down, 1 step to the right, 1 step to the right, go down, 1 step to the right, 1 step to the right. So the depth of the filter has to match the depth of the input, such that every value in the input is multiplied by every value in the filter. So does that make sense as to why in our first one, the depth of the filter was 1, because the depth of the input was also 1, right? In our example, the depth of this image is 1 and the depth of the filter is 1. If the depth of the filter is different here, we now have a mismatch. So in our second application of convolution, since the depth of the input is 20, we need the depth of the filter to match the input such that we can multiply all the values. Is everyone happy with this explanation? So in other words, if we wanted 40 filters, we would need 40 filters that have the exact same depth as the input. So we would have 40 of these filters, and we would apply each of them to this input. Is everyone happy with this? It's a little bit of an uncomfortable idea, and maybe one needs some time to reflect on this. Isaac?
Hello, Doug. Yeah, please help me to understand it. So, applying a filter with a depth of 20 on the output, our first output, how would the result be? Will you have to add them?
Okay. So let's see. Let me use a different color. Let's call this, no, that's a bad color. Let's call this one filter 1. So this one is filter 1. So how does convolution work? We multiply every value in the filter with every value in the input. So this value will multiply with this value. This value will multiply by this value, this one with this one, and so on and so forth. So that was our first depth. Now our second depth, this value will multiply by the value in the second depth. This value will multiply by the value in the depth of 2. This value will multiply by the value in the depth of 3, and we'll do it for all of the 9 ones. Then we'll go to the third channel. This value will multiply by that one, this one by that one, and so on and so forth until eventually we reach the last depth. So it will have its first value, which we multiply by the value there, then the value by the value there. So we have all these many multiplications, and that will generate the first value in the feature map. Right? Now we will take our filter and we will move one stride to the right, and we will do the exact same thing, which will generate the second value in the feature map. So it's the same idea, it's just that there's now an extra depth. So it's the same principle as we saw here. It's just that now, instead of multiplying a one-dimensional, just a matrix with a depth of 1, we now have to worry about multiplying all the values in the extra depth. So does that make sense?
Yes. Sorry, I just wanted to ask this question. I think it's taking us a bit back. What's really the difference between height and depth?
So if we have a grayscale image, a grayscale image is just made up of pixel values, right? So a grayscale image has values between 0 and 255, and the depth is 1. So this image, just like you take a picture on your cell phone, it has a width and a height, right? But if you take a color picture on your cell phone, it has 3 color channels. It has a red color channel, a green color channel, and a blue color channel. So a color picture can be thought of as an object that looks like this, and it has a depth of equal to 3. So we can call the depth as the number of channels, yes. So as you mentioned as Isaac mentioned in the chat. So,
Okay.
So you happy now, Timothy?
Happy, very happy.
Cool. So is everyone happy with how now the convolution is? It's the same idea. We're still striding, we're still multiplying and adding. It's just that now there's the extra depth. So it's just a little bit more complicated, but it's the same idea. We convolve a filter onto an image and it generates feature map values. So filter 1, which has a width and a height and a depth, will generate a feature map, which will have all these values. Now, if we have multiple filters, because I decided I want 40 of them, I'll produce 40 feature maps. In other words, my second convolution will produce an object that has a width and a height, and now the depth will be 40. And you all agreed that initially, if I had 20 filters, that the depth would be 20. So you should agree, similarly, that if I have 40 filters in my second operation, that my depth of my feature map will be 40. So it's a lot to take in, and maybe it requires a bit of time to just ponder about this. But can you let me know if it's somewhat making sense? Okay, what about the rest of you? Feel free to put a thumbs down if it's not making sense, and that's okay. You know, you don't learn this in one day. It's just about trying to convey the ideas, and then you can think about it. Okay, so there were some thumbs up, and then it's just silence. Shane, do you have a question?
So if we're working with an image, then effectively we try and keep it in 2 dimensions because it's an image. So if we have 20 filters, we get a depth of 20. If we have 40 filters, we get a depth of 40. But if we're, say, working with some an input that's in a higher dimension. So if we're looking, for instance, I come from a chemistry background, so if I'm looking at chemistry as my, say, a chemical compound or an electronic state, with each electron as its own input. So I have, say, a rank 40 tensor or something that I have as my input.
A rank how much?
Say, for instance, I have 40 different dimensions that I'm working in. So in a lot of the quantum chemistry applications, you'll have each electron as its own dimension because you can get the superposition of electrons and an atom. So in that case, if your input that you put in is 40 by 40 by 40 as your input, can you then say apply 20 filters? So you get a 40 by 40 by 40 by 20 as your first convolution.
Yeah, so your first filter, let's say your first filter is a 3 by 3. But since your input is 40, your first filter will be 40, a depth of 40. So in our example, it was a grayscale image. So the depth of 1, so the filter was 1. If it's a color image has 3 channels. So if you apply the convolution to a color image, the depth of your filter would be 3. And in your application, the depth is equal to 40. So your first filter will be a depth of 40. So the idea is the depth of the filter will always match what you're applying it to. Okay. And that makes sense because we want to be able to multiply all of the values. Okay. Okay, any other questions? So I think this is the hardest idea to grasp. And for our journey together in this lecture series, it won't get more complicated than this. Okay. So now we've applied essentially our second convolution. Now we have this object that has a depth of 40 and it has a particular width and a particular height. How do we now solve the problem of classification? Because classification requires these nodes and our softmax outputs. So what happens is after applying a number of convolution operations, we flatten the object, and the flattening operation, what it does is it takes your last feature map with whatever depth and width and height, and it essentially converts it into a very long vector. So you can just think of it as you take the first row of values and you put it in, and the second row of values and you put it in, and then you take for the next channel, you put it in, and then you do all the rows, and then you take the next channel and you put it in. So you're essentially converting from an object that has a width and a height and a depth into a very long vector. Okay. And then it's like before, because with our feed-forward neural networks, the input were just numbers. Like we had our data set, remember, it had feature 1, feature 2, up to feature n. And you can think of this as feature 1, this is feature 2, feature 3, feature n. So we essentially can go from an object that has a width and a height and a depth into a very long feature input. which then allows us to use our normal feed-forward neural networks. We have these fully connected layers and softmax output. So this is how the two ideas come together, is we add multiple convolution layers. How many we add is a hyperparameter. So this is where things are messy. You know, how many do you add? But then eventually, when our last output from the convolution layer will produce a feature map, which we can convert into a very long vector, which will connect to all the units, the input units, and then we apply hidden units and our output softmax. So this is how the two ideas combine. Is everyone happy with this? So we're just applying this flattening operation that allows us to go from this complex object into just a very long vector, and we're just copying the values across. That's all that the flattening operation is doing, which creates a long vector. And you can just think of it as how we were talking about before. The first value is feature 1, the second value is feature 2, the third value is feature 3, and so on and so forth. And the last value is our last feature. Are you okay with that or not okay with that? Okay, so 1 thumbs up. Everyone else, are you feeling lost? Okay, 2 thumbs up. Okay, so instead,
Sorry, can I ask?
Yeah.
So here we are saying we've got, let's say we've got a width of 3 and a height of 4, and then a depth of 5, right?
Right.
So for the first, I don't know whether it's a first layer or what, where we look at just height times width. And we are saying it's a matrix, right?
Right.
Yes. So when we convert this one now into a long vector,
right,
are we not taking the first matrix, and then we start to append like matrices for the remaining layers?
Yeah, so you would
join.
take, yeah, so you would look at the first one, and then you would take these values and you would append it to your vector.
Yes.
And so you would take these ones and you would append for the depth of 1 to this. You just keep appending it to the vector. Then you would look at depth of 2, and you would take all the values and append it to the vector.
All right.
You would take depth of 3 and append it to the vector, and so on and so forth until you've reached.
Fine. It's now clear.
Yeah. Right.
All right. Thank you.
Great. Okay. Are there any other questions about this?
Hello.
Yes.
Bob. Hello. So
do you have a question?
So yes, I have a question. So from the diagram that you just drew, where we have the 4x3 and a depth of 5. So when you come to the flattening, we'll be having a 4x3x5 for parameters in the feature in the flattening layer, right?
Yes. Okay. So what's your question?
my question was like, I just a confirmation, like, so we have 4x3x5. So when it comes to the flattening layer, we're having, if you multiply them, that's what 4x5 will be, that's 20x3, that's what 60 parameters within that layer, right?
Yeah.
Okay.
Yeah. So you'll see that if your last feature map is quite big, the flattening operation will generate a lot of parameters. And if each of these are input neurons, you can easily imagine that connecting all of these will generate a huge weight matrix. So if your final feature map is quite big, you'll have a lot of weights in this first hidden layer. So yeah, you will have essentially 5 times 4 times 3 input units, exactly as you said.
Okay, thanks.
Great. So essentially, this is it, right? There's an input image. We take our filter and we apply it to the image. And we apply an activation function, which creates the values in the feature map. And if we have 10 filters, we have a depth of 10 in our feature map. In this diagram, I have like 3 filters, and each filter creates a particular channel in the feature map, the red one, the blue one, and the orange one. And then essentially we're flattening everything. So we're creating a really long vector, and we're connecting all of those things. And what we can do is we can connect all of those things into a softmax output. So if our question was to build a neural network that can classify if the picture contains a cat or not a cat, then we would have 2 softmax units. And this is back to our old lectures, where for an n-class classification problem, we will have n output units. So this is how all of the pieces of the puzzle fit together. We apply convolution, and then we flatten everything, and then we have our normal feed-forward neural networks, and then we have softmax outputs, which generate probabilities that the image contains a cat or not a cat. So hopefully, the way this was explained to you, you can see now how all the pieces of the puzzle fit together. So essentially, the convolution layers try to learn useful visual features, right? Because that's the purpose of the filters, is to create these feature maps, which are hopefully useful. And then it's passed to the feed-forward neural network part, which is responsible for doing a classification. So the convolution layers learn weights in the filters, and then the resulting feature map is passed on to the fully connected layers, which learn weights and uses nonlinear activation functions to eventually perform a classification. So hopefully you can appreciate and are okay with how all of the previous stuff we talked about can fit into solving a convolution problem. Okay. So there is one more type of layer that is used quite frequently in CNNs, and it's quite easy to explain. So we don't have a lot of time left, but it's quite an easy one to explain. And it's called max pooling. And the way max pooling does it also has a width and the height. And let's say here the width and the height is 2 by 2. So what we do is we take a 2 by 2 window and we put it on the input, and we ask ourselves, what is the largest value? Here the largest value is 20, and then we put that as our first value in the feature map. Now let's say I applied a stride of 2, which means I jump by 2 steps. Now I take my 2 by 2 window and I ask myself, what's the largest value? It's 13, and that's the next value in the feature map. Now I can't jump any more to the right, so I go downwards, and since my stride is 2, I take 2 steps downwards. And now I ask myself, what's the largest value? It's 11, so that's the value in the feature map. And then since my stride is 2, I jump 2 steps to the right. I ask myself, what's the largest value? It's 20, and that's the next value in the feature map. So what max pooling does is it extracts the largest value in a predefined window. So you say, I want my max pooling to be 2 by 2, 3 by 3. It's a hyperparameter. And you also decide on the stride. And the idea with this is we're trying to reduce the spatial size of the layers. So we're compressing the width and the height. We're not compressing the depth. So max pooling is applied individually and independently to each channel in the input. So each channel here, we say, we place a little window and we say, what's the maximum value? Then we move our window and then we ask ourselves, what's the maximum value? So the result of this is if we have our feature map, which has a depth of D, what max pooling does is, let's say this is W and H. What max pooling does is it makes it smaller along the width and the height, but the depth is the same. So the depth is the same, but now we have a W prime and H prime, which is smaller than the original H and W. So it's trying to extract the maximum information, what's useful. So some of these pixel values might not be useful. So we try to extract the maximum, and as a result, we are compressing the width and the height. And if you were comfortable with what we talked about here, that if you have a large feature map, you have a large number of inputs, then this will make sense why we would want to do this, to compress it, to make it a bit smaller. And we're essentially extracting the most useful information by assuming that a large value is a useful value. And anything that is not large, we are losing that information. So max pooling is just compressing along the width and the height by extracting maximum values. Is everyone okay with that? So here you can see we're just extracting maximum values, and I'm drastically reducing from a 4x4 to a 2x2 by using a stride of 2. I'm losing a lot of information. I'm retaining the maximum values, but as a result of this, my feature map is a little bit smaller. And that's the other type of layer that is used in convolution layers is max pooling. So essentially we want to combine all of these together, and how we would combine it is I made this little thing. We would have an input, and then we could have 1 or more convolution layers, and we could have 0 or 1 max pooling layers. And then we can do this 1 or more times. So here you'll see that we have a lot of decisions to make. And this refers to the architecture of the CNN. Are we going to create a complicated architecture and maybe have overfitting? Or are we going to have a simple architecture and maybe have underfitting? So to give you an idea, since we have 5 minutes, this is a simple CNN. We have our input, we have 1 convolution, and we have our output unit. So here you can see that I've done 1 convolution. I didn't do more. I didn't use max pooling. So I had 1 convolution, had 0 max pooling. I only did this once. And then I had, I didn't create any fully connected layers. I just created my output layer. So this is like the absolute most simple CNN with 1 convolution and an output softmax layer. then you can add a bit more complexity. You can say, I want one convolution, I want max pooling to compress the width and the height, and then I want another convolution, and then I want max pooling. So you can gradually add complexity slowly but surely. Here you can see that I have a convolution, max pooling, convolution, and now I'm adding a fully connected layer before my output layer. So you know, the architectures is up to you, and that's what makes it a little bit difficult. How do you optimize for your architecture? And this is an active area of research in deep learning, is trying to find ways to optimize these neural networks. But is everyone okay with basically the idea of we can start simple and gradually add complexity? So Matt, you have a hands up.
Yeah, I just have a question, or trying to see if I understand it correctly in terms of the architecture. So I've read a lot of times that with CNNs, there's nice things to capture local and global correlations. So I'm just wondering if the act of the convolutions helps you with capturing local correlations in your image and your data, and then the act of fully connecting everything again is what allows you to capture the global, you know, if it connects that way to that idea.
Yeah, you can think of it that way, yeah.
Okay. Yeah, thanks, that's it.
So, so we are out of time for today, but hopefully the key points you were able to grasp in terms of the idea of a filter and the idea of convolution, how we convolve a filter to an image. And maybe in the last 10 seconds, I'll just say that there is no expectation that one can understand this in one lecture. So this, you know, requires weeks of work, but the take-home messages are about some of the fundamental ideas of how do we convolve, and how do we, you know, the idea of that the filter depth is equal to the previous depth, and that we can then apply the fully connected layers to our feature map, and then have a classification model. So those are the key things. And if you're comfortable with the high level ideas, then I think that's okay for today.
Yeah, Emmanuel, thank you very much for another fantastic lecture. And I was very pleased to see that everybody engaged a lot today. That's excellent. So thank you very much for making it interactive and making sure that everybody gets involved. Yeah. No, so thank you very much. And I think just to finish today with the usual adverts. Yeah. At 2 o'clock we have lecture 4 of Professor Jan Elitze on mathematical proofs with Python. Yeah, and so we will meet again just before 2. And the last lecture of Emmanuel will also be the last lecture, if I remember correctly, let me check, of the summer school. So please don't forget to join us on Friday afternoon. And after the lecture of Emmanuel on Friday, we will have a small closing function, yeah, where we want to award some of the book prizes that we promised, yeah. And you know, and I will have to engage with Emmanuel for the nominations of the book prize for his lecture, yeah. So please on Friday, but please after the lecture stay online, and we will we have a small probably 20 minutes, half an hour maximum closing ceremony. So thank you very much, everyone. Thank you very much, Emmanuel. We'll see you latest on Friday again. Thank you very much.
Thank
Please
you.
let me know before then if you have a candidate or two. Yeah. Yeah.
Great.
I
Thank
have
you, everyone.
made some notes as well, but we can compare later. Yeah, excellent.
Great. Have a great day, everyone.
Thank you very much. Bye. Bye. All the
Bye.
best.